Hello, Namaste. Myself Ankita Shreya Prasad, and you are listening to along with our NCERT 11th and 12th audio video book presented by ArtSkill Passion. Unit 1, The Solid State. From our earlier studies, we know that liquids and gases are called fluids because of their ability to flow. The fluidity in both of these states is due to the fact that the molecules are free to move about. On the contrary, the constituent particles in solids have fixed positions and can only oscillate about their mean positions. This explains the rigidity in solids. These properties depend upon the nature of constituent particles and the binding forces operating between them. The correlation between structure and properties helps in the discovery of new solid materials with desired properties. For example, carbon nanotubes are new materials that have potential to provide materials that are tougher than steel, lighter than aluminum, and have more conductive property than copper. Such materials may play an expanding role in future development of science and society. Some other materials which are expected to play an important role in future are high temperature and superconductors, magnetic materials, biodegradable polymers for packaging, biocompliant solids for surgical implants, etc. Thus, the study of this state becomes more important in the present scenario. In this unit, we shall discuss different possible arrangement of particles resulting in several types of structures and explore why different arrangements of structural units lend different properties to solids. We will also learn how these properties get modified due to the structural imperfections by the presence of impurities in minute amounts. 1.1 General characteristics of solids. In class 11th, you have learned that matter can exist in three states, namely solid, liquid, and gas, under a given set of conditions of temperature and pressure. Which of these would be the most stable state of a given substance depends upon the net effect of two opposing factors. These are intermolecular forces, which tend to keep the molecules or atoms or ions closer, and the thermal energy, which tends to keep them apart by making them move faster. At sufficiently low temperature, the thermal energy is low and intermolecular forces bring them so close that they cling to another and occupy fixed positions. These can still oscillate about their mean positions and the substance exists in solid state. The following are the characteristics properties of the solid state. First, they have definite mass, volume, and shape. Second, intermolecular distances are short. Third, intermolecular forces are strong. Fourth, their constituent particles, atom molecules or ions have fixed positions and can only oscillate about their mean positions. Fifth, they are incompressible and rigid. 1.2 Amorphous and crystalline solids. Solids can be classified as crystalline and amorphous on the basis of the nature of order present in the arrangement of their constituent particles. A crystalline solids usually consist of a large number of small crystals, each of them having a definite characteristic geometrical shape. The arrangement of constituent particles, atoms, molecules, or ions in crystal is ordered and repetitive in 3 dimensions. If we observe the pattern in the one region of the crystal, we can predict accurately the positions of particles in an other region of the crystal. However far they may be from the place of observation, thus crystal has long range order, which means that there is regular pattern of arrangements of particles which repeat itself periodically over the entire crystal. Sodium chloride and quartz are typical examples of crystalline solids. Glass, rubber and many plastics do not form crystals when their liquids solidify on cooling. These are called amorphous solids. The term amorphous comes from the Greek word amorphous, meaning no form. The arrangement of constituent particles, atom, molecules or ions in such a solid has only short range order. In such arrangement, a regular and periodically repeating pattern is observed over short distances only. Regular patterns are scattered and in between the arrangement is disordered. The structures of crust and crystalline quartz glass amorphous are shown in Figure 1.1. Figure 1.1. Two-dimensional structure of A. Quartz and B. Quartz glass. While the two structures are almost identical, yet in the case of amorphous quartz glass there is no long range order. The structure of amorphous solids is similar to that of liquids due to the differences in the arrangement of the constituent particles. The two types of solids differ in their properties. Crystalline solids have a sharp melting point, a characteristic temperature they melt abruptly and become liquid. On the other hand, amorphous solids soften, melt and start flowing over a range of temperature and can be molded and blown into various shapes. Amorphous solids have the same structural features as liquids and are conveniently regarded as extremely viscous liquids. They may become crystalline at some temperature. Some glass objects from ancient civilizations are found to be milky in appearance because of some crystallizations. Like liquid, amorphous solids have a tendency to flow, though very slowly. Therefore, sometimes these are called pseudo-solids or supercooled liquids. Amorphous solids are isotropic in nature. Their properties such as mechanical strength, refractive index and electrical conductivity etc. are same in all directions. It is because there is no long range order in them and arrangement of particles is not definite along all the directions. Hence, the overall arrangement becomes equivalent in all directions. Therefore, value of any physical property would be same along any directions. Crystalline solids are anisotropic in nature, that is, some of the physical properties like electrical resistance or refractive index show different values when measured along different directions in the same crystal. This arises from different arrangement of particles in different directions. This is illustrated in Figure 1.2. Figure 1.2. Anisotropy in crystals is due to different arrangement of particles along different directions. This figure shows a simple two-dimensional pattern of arrangement of two kinds of atoms. Mechanical properties such as resistance to shearing stress might be quite different in two directions indicated in the figure. Deformation in CD direction displaces row which has two different types of atoms, while in AB direction rows made of one type of atom are displaced. The difference between the crystalline solids and amorphous solids are summarized in Table 1.1. Table 1.1. Distinction between crystalline and amorphous solids. Crystalline solid shape. Definite characteristic geometrical shape. Amorphous solids. Irregular shape. Melting point. Crystalline solids melting at sharp characteristic temperature. Melting point in amorphous solids gradually softens over a range of temperature. Cleavage property. Crystalline solids, when cut with a sharp edged tool, they split into two pieces and the newly generated surfaces are plain and smooth. Amorphous solids, when cut with a sharp edged tool, they cut into two pieces with irregular surfaces. Heat of fusion. Crystalline solids, they have a definite characteristic enthalpy of fusion. Amorphous solids, they do not have definite enthalpy of fusion. Anisotropy. Crystalline solids, anisotropic in nature. Amorphous solids, isotropic in nature. Nature. Crystalline solids are true solids. Amorphous solids are pseudo-solids or supercooled liquids. Order in arrangement of constituent particles. Crystalline solids, long range order. Amorphous solids, only short range order. Beside crystalline and amorphous solids, there are some solids which apparently appear amorphous but have microcrystalline substructures. These are called polycrystalline solids. Metals often occur in polycrystalline conditions. Individual crystals are randomly oriented, so metallic sample may appear to be isotropic, even though a single crystal is anisotropic. Amorphous solids are useful materials. Glass, rubber and plastics and many applications in our daily lives. Amorphous silicon is one of the best photovoltaic material available for conversion of sunlight into electricity. 1.3 Classification of crystalline solids. In section 1.2 we have learnt about amorphous substances and that they have only short range order. However, most of the solid substances are crystalline in nature. For example, all the metallic elements like iron, copper and silver. Non-metallic elements like sulfur, phosphorus and iodine and compounds like sodium chloride, zinc sulfate and naphthalene form crystalline solids. Crystalline solids can be classified in various ways. The method depends on the purpose in hand. Here we will clarify crystalline solids on the basis of nature of intermolecular forces or bonds that hold the constituent particles together. These are first, van der Waals forces, second, ionic bond, third, covalent bonds and fourth, metallic bonds. On this basis, crystalline solids are classified into four categories, that is molecular, ionic, metallic and covalent solids. Let us now learn about these categories. 1.1 Molecular solids. Moleculars are the constituent particles of molecular solids. These are further subdivided into following categories. First, nonpolar molecular solids. They comprises either atoms, for example argon and helium, or the molecules formed by non-polar covalent bonds, for example H2, Cl2 and I2. In these solids, the atoms molecules are held by weak dispersion forces or London forces, about which you have learnt in class 11th. These solids are soft and non-conductors of electricity. They have low melting points and are usually in liquid or gaseous state at room temperature and pressure. Second, polar molecular solids. The molecules of substances like HCl, SO2, etc. are formed by polar covalent bonds. The molecules in such solids are held together by relatively stronger dipole-dipole interactions. These solids are soft and non-conductors of electricity. Their melting points are higher than those of non-molecular solids. Yet, most of these are gases or liquids under room temperature and pressure. Solid SO2 and solid NH3 are some examples of such solids. Hydrogen bonded molecules. Molecular solids. The molecules of such solids contain polar covalent bonds between H and F, O or N atoms. Strongly hydrogen bonding binds molecules of such solids like H2O. They are non-conductors of electricity. Generally, they are volatile liquids or soft solids under room temperature and pressure. 1.3.2 Ions are the constituent particles of ionic solids. Such solids are formed by the three-dimensional arrangements of cations and anions bound by strong Coulombic electrostatic forces. These solids are hard and brittle in nature. They have high melting and boiling points. Since the ions are not free to move about, they are electrical insulators in the solid state. However, in the molten state or when dissolved in water, the ions become free to move about and they conduct electricity. 1.3.3 Metallic solids. Metals are orderly collection of positive ions surrounded by and held together by a sea of free electrons. These electrons are mobile and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards the sea of mobile electrons. These free and mobile electrons are responsible for high electrical and thermal conductivity of metals. When an electric field is applied, these electrons flow through the network of positive ions. Similarly, when heat is supplied to one portion of a metal, the thermal energy is uniformly spread throughout by free electrons. Another important characteristics of metals is their luster and color in certain cases. This is also due to the presence of free electrons in them. Metals are highly malleable and ductile. 1.3.4 Covalent or network solids. A wide variety of crystalline solids of non-metals result from the formation of covalent bonds between adjacent atoms throughout the crystal. They are also called gain molecules. Covalent bonds are strong and directional in nature. Therefore, atoms are held very strongly at their positions. Such solids are very hard and brittle. They have extremely high melting point and may even decompose before melting. They are insulator and do not conduct electricity. Diamond, figure 1.3, and silicon carbide are typical examples of such solids. Although graphite, figure 1.4, also belong to this class of crystalline, but it is soft and is a conductor of electricity. Its exceptional properties are due to its typical structure. Carbon atoms are arranged in different layers, and in each atom is covalently bonded to three of its neighboring atoms in the same layer. The fourth valence electron of each atom is present between different layers and is free to move about. These free electrons make graphite a good conductor of electricity. Different layers can slide one over the other. This makes graphite a soft solid and a good solid lubricant. The different properties of the four types of solids are listed in Table 1.2. Table 1.2. Different types of solids. Types of solid. First, molecular solids. Non-polar, constituent particles, molecules. Bonding attractive forces, dispersion or London forces. Example, ArCCl4, H2I2, CO2. Physical nature, soft. Electrical conductivity, insulator. Melting point, very low. Polar, dipole-dipole interactions. Examples, HCl, SO2. Physical nature, soft. Electrical conductivity, insulator. Melting point, low. Hydrogen, bonded. Bonding attractive forces, hydrogen bonding. Example, H2O, ice. Physical nature, hard. Electrical conductivity, insulator. Melting point, low. Ionic solids, ions. Bonding attractive forces, Coulombic or electrostatic. Examples, NaCl, MgO, ZnS, CaF2. Physical nature, hard but brittle. Electrical conductivity, insulator in solid state but conductors in molten state and in aqueous solutions. Melting point, high. Metallic solids, constituent particles, positive ions in a sea of delocalized electrons. Bonding attractive forces, metallic bonding. Example, Fe, Cu, Ag, Mg. Physical nature, hard but malleable and ductile. Electrical conductivity, conductors in solid state as well as in molten state. Melting point, fairly high. Fourth, covalent or network solids. Constituent particles, atoms. Covalent bonding. Examples, SiO2, quartz, SiC, C, diamond, AIN, C, graphite. It's hard and soft. Electrical conductivity, insulators and conductor exceptions. Very high. 1.4. Crystal lattice and unit cells. You must have noticed that when tiles are placed to cover a floor, a repeated pattern is generated. If after setting tiles on the floor, we mark a point at same location in all the tiles. Example, center of the tile, and see the marked positions only ignoring the tiles, we obtain a set of points. This set of points is scaffolding on which pattern has been developed by placing tiles. This scaffolding is a space lattice on which two-dimensional pattern has been developed by placing structural units on a set of points, that is, tile in this case. The structural unit is called basis or motif. When motifs are placed on points in space lattice, a pattern is generated in crystal structure. Motif is a molecule, atom or ion. A space lattice, also called a crystal lattice, is the pattern of points representing the locations of these motifs. In other words, space lattice is an abstract scaffolding crystal structure. When we place motifs in an identical manner on the points of space lattice. Figure 1.5. A. Motif. A. Motif to make crystal structure. B. Space lattice, two-dimensional. B. Space lattice or a crystal lattice, two-dimensional. C. Hypothetical, two-dimensional crystal structure. C. Hypothetical two-dimensional crystal. We get crystal structure. Figure 1.5 show a motif, a two-dimensional lattice and a hypothetical two-dimensional crystal structure obtained by placing motif in the two-dimensional lattice. Spatial arrangement of lattice points give rise to different types of lattice. Figure 1.6 shows the arrangement of points in two different lattices. Figure 1.6 Arrangement of points in two different lattices, lattice A and lattice B. In the case of crystalline solid, space lattice is a three-dimensional array of points. The crystal structure is obtained by associating structural motifs with lattice points. Each repeated basis or motif has same structure and same spatial orientation as other one in the crystal. The environment of each motif is same throughout the crystal except for one surface. Following are the characteristics of a crystal lattice. A. Each point in lattice is called lattice point or lattice site. B. Each point in crystal lattice represents one constituent particles which may be an atom, a molecule, group of atoms or an ion. C. Lattice points are joined by straight lines to bring out geometry of the lattice. We need only a small part of the space lattice of a crystal to specify crystal completely. This small part is called unit cells. One can choose unit cell in many ways. Normally, that cell is chosen which has perpendicular sides of shorter length, and one can construct entire crystal by translation displacement of the unit cell in 3 dimensions. Figure 1.7 shows the movement of unit cell of two-dimensional lattice to construct entire crystal structure. Also, unit cells have shapes such that these fills the whole lattice without leaving space between the cells. Figure 1.7 Generating hypothetical two-dimensional crystal structure by shifting square in the direction of arrows. In two-dimensional, a parallelogram with side of length A and B and an angle R between these sides is chosen as unit cell. Possible unit cells in two dimensions are shown in figure 1.8. Figure 1.8 Possible unit cells in two dimensions. Figure 1.9 A portion of three-dimensional cubic space of lattices and its unit cell. Figure 1.10 Illustration of parameters of unit cell. A portion of three-dimensional crystal lattices and its unit cell is shown in figure 1.9. In the three-dimensional crystal structure, unit cell is characterized by: first, its dimensions along the three edges A, B and C. These edges may not be mutually perpendicular. Second, angle between these edges: alpha between B and C, beta between A and C, and gamma between A and B. Thus, a unit cell is characterized by 6 parameters: A, B, C, alpha, beta, gamma. These parameters of typical unit cells are shown in figure 1.10. 1.4.1 Primitive uncentered unit cells. Unit cells can be broadly divided into two categories: primitive uncentered unit cells. A. Primitive unit cell. When constituent particles are present only on the corner positions of a unit cell, it is called primitive unit cells. B. Centered unit cells. When unit cell contains one or more constituent particles present at positions other than corners in addition to those at corners, it is called a centered unit cell. Centered unit cells are of three types. First, body-centered unit cells. Such a unit cell contains one constituent particles, atoms, molecules or ions at its body center beside the ones that are at its corners. Second, face-centered unit cells. Such a unit cells contain one constituent particles present in center of each face beside the ones that are at its corner. Third, end-centered unit cells. In such a unit cell, one constituent particle is present at the center of any two opposite faces beside the ones present at its corners. Inspection of a wide variety of crystal leads to the conclusion that all can be regarded as conforming to one of the 7 regular figures. These basis regular figures are called 7 crystal systems. To which system a given crystal belongs to is determined by measuring the angles between its faces and deciding how many axes are needed to define the principal feature of these shapes. Figure 1.11 shows several crystal systems. Figure 1.11 7 crystal system: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. A French mathematician, Bravais, showed that there are only 14 possible 3-dimensional lattices. These are called Bravais lattices. Unit cells of these lattices are shown in the following box. The characteristics of their primitive unit cells along with the centered unit cells that they can form have been listed in table 1.3. 7 primitive unit cells and their possible variations as centered unit cells. First, crystal system cubic. Possible variation: primitive, body center, face centers. Axial distances or edge length: A is equal to B, B is equal to C. Axial angles: alpha is equal to beta, beta is equal to gamma is equal to 90 degrees. Examples: NaCl, zinc, bendite and Cu. Tetragonal. Possible variation: primitive, body centered. Axial distances or edge length: A is equal to B, B is not is equal to C. Axial angles: alpha is equal to beta is equal to gamma is equal to 90 degrees. Example: white, tin, SnO2, PiO2, CaSO4. Orthorhombic. Primitive, body centered, face centered, end centered. Axial distances: A is not is equal to B, B is not is equal to C. Axial distances: alpha is equal to beta is equal to gamma is equal to 90 degrees. Example: rhombic sulfur, KNO3, BaSO4. Hexagonal. Possible variations: primitive, body centered, face centered, and end centered. Edge length, A is not is equal to B, B is not is equal to C. Axial angles, alpha is equal to beta is equal to gamma is equal to 90 degrees. Graphite. Example, graphite ZnO CdS. Rhombohedral or trigonal. Possible variations, primitive. Edge length, alpha is equal to beta is equal to gamma is equal to 90 degrees. Edge length, A is equal to B is equal to C. Example, calcite CaCO3 HgS cinnabar. Monoclinic. Possible variations, primitive and end centered. Axial distance, A is not is equal to B, B is not is equal to C. Axial angles, alpha is equal to gamma is equal to 90 degrees, beta is not is equal to 90 degrees. Examples, monoclinic sulfur Na2SO4 0.10 H2O. Triclinic. Possible variations, primitive. Axial distance, A is not is equal to B, B is not is equal to C. Axial angles, alpha is not is equal to beta, beta is not is equal to gamma, gamma is not is equal to 90 degrees. Example, K2Cr2O7 CuSO4 0.5 H2O, H3 and BO3. 1.5 Number of atoms in a unit cell. We know that any crystal lattice is made up of a very large number of unit cells, and every lattice point is occupied by one constituent particle, atom, molecules or ions. Let us now work out what portion of each particle belongs to a particular unit cell. We shall consider three types of cubic unit cells, and for simplicity assume that the constituent particle is an atom. 1.5.1 Primitive cubic unit cell. Primitive cubic unit cell has atoms only at its corner. Each atom at a corner is shared between 8 adjacent unit cells as shown in figure 1.12. 4 unit cells in the same layer and 4 unit cells of the upper or lower layer. Therefore, only 1/8 of an atom or molecules or ions actually belong to a particular unit cell. In figure 1.3, a primitive cubic unit cell has been depleted in 3 different ways. Each small pair in figure 1.13a represent only the center of particle occupying that position, not its actual size. Such structures are called open structures. The arrangement of particles is easier to follow in open structures. Figure 1.13b depicts space-filling representation of the unit cell with actual particle size, and figure 1.13c shows the actual portions of different atoms present in a cubic unit cell. Figure 1.12. In a simple cubic unit cell, each corner atom is shared between 8 unit cells. In all, since each cubic unit cell has 8 atoms on its corner, the total number of atoms in one unit cell is 8 into 1/8 is equal to 1 atom. Figure 1.13. A primitive cubic unit cells: A. Open structure, B. Space-filling structure, C. Actual portions of atoms belonging to one unit cells. 1.5.2 Body-centered cubic unit cell. A body-centered cubic BCC unit cell has an atom at each of its corner and also one atom at its body center. Figure 1.14 depicts A. Open structure, B. Space-filling model, and C. The unit cell with portions of atoms actually belonging to it. It can be seen that the atom at the body center wholly belongs to the unit cell in which it is present. Thus, in a body-centered cubic BCC unit cell, first 8 corners into 1 by 8 per corner atoms is equal to 8 into 1 by 8 is equal to 1 atom. Second, 1 body center atom is equal to 1 into 1 is equal to 1 atoms. Therefore, total number of atoms per unit cell is equal to 2 atoms. Figure 1.14. A body-centered cubic unit cell. A. Open structure. B. Space-filling structure. C. Actual portions of atoms belonging to one unit cell. 1.5.3. Face-centered cubic unit cell. A face-centered cubic FCC unit cell contains atoms at all the corners and the center of all the faces of the cube. It can be seen in figure 1.15 that each atom located at the face center is shared between two adjacent unit cells and only 1 by 2 of each atoms belong to a unit cell. Figure 1.16 depicts a open structure, B. Space filling model, C. The unit cell with portions of atom actually belonging to it. Thus, in face-centered cubic FCC unit cells, first 8 corner atoms into 1 by 8 atom per unit cell is equal to 8 into 1 by 8 is equal to 1 atom. Second, 6 face-centered atoms into 1 by 2 atom per unit cell is equal to 6 into 1 by 2 is equal to 3 atoms. Therefore, total number of atoms per unit cell is equal to 4 atoms. Figure 1.15. An atom at face center of unit cell is shared between two unit cells. Figure 1.16. A face centered cubic unit cell. A. Open structure. B. Space filling structure. C. Actual portions of atoms belonging to one unit cell. 1.6. Close packed structure. In solids, the constituent particles are close packed, leaving the minimum vacant space. Let us consider the constituent particles as identical hard spheres and build up the three-dimensional structures in 3 steps. A. Close packing in one dimension. There is only one way of arranging spheres in one-dimensional close packed structure, that is to arrange them in a row and touching each other. Figure 1.17. Figure 1.17 Close packing of spheres in one dimension. In this arrangement, each sphere is in contrast with two of its neighbors. The number of nearest neighbors of a particle is called its coordination number. Thus, in one-dimensional close-packed arrangement, the coordination number is 2. B. Close packing in 2 dimensions. 2-dimensional close-packed structure can be generated by placing the rows of close-packed spheres. This can be done in 2 different ways. First, the second row may be placed in contact with the first one such that the spheres of the second row are exactly above those of the first row. The spheres of the 2 rows are aligned horizontally as well as vertically. If we call the first row as A-type row, the second row being exactly the same as the first one is also of A-type. Similarly, we may place more rows to obtain AA type of arrangement as shown in figure 1.18a. Figure 1.18a. Square close packing. B. Hexagonal close packing of spheres in 2 dimensions. In this arrangement, each sphere is in contact with 4 of its neighbors. Thus, 2-dimensional coordination number is 4. Also, if the centers of these 4 immediate neighboring spheres are joined, a square is formed. Hence, this packing is called square close packing in 2 dimensions. Second, the second row may be placed above the first one in staggered manner such that its spheres fit in depression of the first row. If the arrangement of the spheres in the first row is called A type, one in the second row is different and may be called B type. When the third row is placed adjacent to the second in staggered manner, its spheres are aligned with those of the first layer. Hence, this layer is also of A type. The spheres of similarly placed fourth row will be aligned with those of the second row, B type. Hence, this arrangement is of AB type. In this arrangement, there is less free space and this packing is more efficient than the square close packing. Each sphere is in contact with 6 of its neighbors and the 2-dimensional coordination number is 6. The centers of these 6 spheres are at the corners of regular hexagon, figure 1.18b. Hence, this packing is called 2-dimensional hexagonal close packing. It can be seen in figure 1.18b. That in this layer there are some voids, empty spaces. These are triangular in shape. The triangular voids are of different types. In one row, the apex of the triangles are pointing upwards and in the next layer downwards. C. Close packing in 3 dimensions. All real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers one above the other. The last section we discussed close packing in 2 dimensions, which can be of 2 types: square close packed and hexagonal close packed. Let us see what types of 3-dimensional close packing can be obtained from these. First, 3-dimensional close packing form 2-dimensional square close packed layers. While placing the second square close packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first layer such that the sphere of the upper layer are exactly above those of the first layer. In this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically as shown in figure 1.19. Similarly, we may place more layers one above the other. If the arrangement of sphere in the first layer is called A type, all the layers have the same arrangement. Thus, this lattice has AAA and so on type pattern. The lattice thus generated is the simple cubic lattice and its unit cell is the primitive cubic unit cell. See in figure 1.19. Figure 1.19. Simple cubic lattice formed by AAA and so on arrangement. Second, 3-dimensional close packing from 2-dimensional hexagonal close packed layers. 3-dimensional close packed structures can be generated by placing layer one over the other. A. Placing second layer over the first layer. Let us take a 2-dimensional hexagonal close packed layer A and place a similar layer above it, such that the sphere of second layer are placed in depressions of the first layer. Since the sphere of the two layers are aligned differently, let us call the second layer as B. It can be observed from figure 1.12 that all the triangular voids of the first layer are not covered by the sphere of the second layer. This gives rise to different arrangements. Whenever a sphere of second layer is above the void of the first layer or vice versa, a tetrahedral void is formed. These voids are called tetrahedral voids because of a tetrahedron is formed when the centers of these four spheres are joined. They have been marked as T in figure 1.20. One such void has been shown separately in figure 1.12. Figure 1.20. A stack of two layers of close packed spheres and voids generated in them. T is equal to tetrahedral void. O is equal to octahedral voids. Figure 1.12. 1.21. Tetrahedral and octahedral voids. A. Top view. B. Exploited side view. And C. Geometrical shape of the void. At other places, the triangular voids in the second layer are above the triangular voids in the first layer, and the triangular shapes of these do not overlap. Over them, one of them has the apex of the triangle pointing upward and the other downwards. These voids have been marked as O in figure 1.20. Such voids are surrounded by 6 spheres and are called octahedral voids. One such void has been shown separately in figure 1.21. The number of these two spheres of voids depends upon the number of close packed spheres. Let the number of close packed spheres be n. Then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. B. Placing third layer over this second layer. When third layer is placed over the second, there are two possibilities. First, covering tetrahedral voids. Tetrahedral voids of the second layer may be covered by spheres of the third layer. In this case, the spheres of the third layer are exactly aligned with those of the first layer. Thus, the pattern of spheres is repeated in alternate layers. This pattern is often written as AB, AB, and so on pattern. This structure is called hexagonal close packed HCP structure, figure 1.22. This sort of arrangement of atoms is found in many metals like magnesium and zinc. Figure 1.22. A hexagonal cubic close packing exploited view showing stacking of layers of spheres. B. 4 layers stacked in each case, and C. Geometry of packing. Figure 1.23. ABC, and so on arrangement of layers when octahedral void is covered. B. Fragment of structure formed by this arrangement resulting in cubic close packed CCP or face centered cubic FCC structure. Second, covering octahedral voids. The third layer may be placed above the second layer in a manner such that its spheres cover the octahedral voids. When placed in this manner, the spheres of the third layer are not aligned with those of either the first or the second layer. This arrangement is called C-type. Only when fourth layer is placed, its spheres are aligned with those of the first layer as shown in figure 1.22 and 1.23. This pattern of layers is often written as ABC, ABC, and so on. This structure is called cubic close packed CCP or face centered cubic FCC structure. Metals such as copper and silver crystallize in this structure. Both these type of close packing are highly efficient, and 74% space in crystal is filled. In either of them, each sphere is in contact with 12 spheres. Thus, the coordination number is 12 in either of these two structures. 1.6.1 Formula of a compound and number of voids filled. Earlier in the section, we have learned that when particles are close packed, resulting in either CCP or HCC structure, two types of voids are generated. While the number of octahedral voids present in a lattice is equal to the number of close packed particles, the number of tetrahedral voids generated is twice this number. In ionic solids, the bigger ions, usually anions, form the close packed structure, and the smaller ions, usually cations, occupy the voids. If the latter ion is small enough, the tetrahedral voids are occupied. If bigger than octahedral voids, all octahedral or tetrahedral voids are not occupied in the given compound. The fraction of octahedral or tetrahedral voids that are occupied depends upon the chemical formula of the compound, as can be seen from the following example. 7.1 Packing efficiency. In whatever way the constituent particles, atom molecules or ions are packed, there is always some free space in the form of voids. Packing efficiency is the percentage of total space filled by the particles. Let us calculate the packing efficiency in different types of structures. 1.7.1 Packing efficiency in HCP and CCP structures. Both types of close packing, HCP and CCP, are equally efficient. Let us calculate the efficiency of packing in CCP structure. In figure 1.24, let the unit cell edge length be A and face diagonal AC is equal to B. In triangle ABC, AC square B square is equal to BC square plus AB square is equal to A square plus A square is equal to 2A square, or B is equal to root 2A. If R is the radius of this sphere, we find B is equal to 4R is equal to root 2A, or A is equal to 4R divided by root 2 is equal to 2 root 2R. We can also write R is equal to A divided by 2 root 2. We know that each unit cell in the CCP structure has effectively 4 spheres. Total volume of 4 spheres is equal to 4 into 4 divided by 3 pi r cube, and volume of the cube is a cube, or 2 root 2 r whole cube. Therefore, packing efficiency is equal to volume occupied by 4 spheres in the unit cell into 100% divided by total volume of the unit cell is equal to 4 into 4 by 3 pi r cube into 100% divided by 2 root r is equal to 16 divided by 3 pi r cube into 100% divided by 16 root 2 r cube is equal to 74%. Figure 1.24 Cubic close packing. Other sides are not provided with spheres for sake of clarity. 1.7.2 Efficiency of packing in body-centered cubic structure. From figure 1.25, it is clear that the atom at the center will be in touch with the other two atoms diagonally arranged. Figure 1.25 Body-centered cubic unit cell sphere along the body diagonal are shown with the solid boundaries. In triangle EFD, B square is equal to A square plus A square is equal to 2A square. B is equal to root 2A. Now in triangle AFD, C square is equal to A square plus B square is equal to A square plus 2A square is equal to 3A square. C is equal to root 3A. The length of the body diagonal C is equal to 4R, where R is the radius of the sphere atom as all the three spheres along the diagonal touch each other. Therefore, root 3a is equal to 4r, a is equal to 4r divided by root 3. Also, we can write r is equal to root 3 by 4a. In this type of structure, total number of atoms is 2 and their volume is 2 into 4 divided by 3 pi r cube. Volume of the cube a cube will be equal to 4 divided by root 3 r whole to the power cube, or a cube is equal to 4 by root 3 r whole cube. Therefore, packing efficiency is equal to volume occupied by two spheres in the unit cell into 100% divided by total volume of the unit cell is equal to 2 into 4 divided by 3 pi r cube into 100% divided by 4 by root 3 r whole to the power cube is equal to 8 by 3 into pi r cube into 100% divided by 64 divided by 3 root 3 r cube is equal to 68%. 1.7.3 Packing efficiency in simple cubic lattice. In a simple cubic lattice, the atoms are located only on the corners of the cube. The particles touch each other along the edge. Figure 1.26. Thus, the edge length or the side of a cube A and the radius of each particle R are related as A is equal to 2R. The volume of the cubic unit cell is equal to A cube is equal to 2R whole cube is equal to 8R cube. Since a simple cubic unit cell contains only one atom, the volume of the occupied space is equal to 4 divided by 3 pi r cube. Figure 1.26 Simple cubic unit cells, the spheres are in contact with each other along the edge of the cube. Therefore, packing efficiency is equal to volume of one atom divided by volume of cubic unit cell into 100% is equal to 4 by 3 pi r cube divided by 8 r cube into 100 is equal to pi by 6 into 100 is equal to 52.36% is equal to 52.4%. Thus, we may conclude that CCP and HCP structures have maximum packing efficiency. 1.8 Calculations involving unit cell dimensions. From the unit cell dimension, it is possible to calculate the volume of unit cell. Knowing the density of the metal, we can calculate the mass of atom in the unit cell. The determination of mass of a single atom gives an accurate method of determination of Avogadro's constant. Suppose H length of unit cell of a cube crystal determined by X-ray diffraction is AD, the density of the solid substances, and M the molar mass in case of cubic crystal. Volume of unit cell is equal to A cube. Mass of the unit cell is equal to number of atoms in unit cell into mass of each atom is equal to Z into M. Here, Z is the number of atoms present in one unit cell and M is the mass of a single atom. Mass of an atom present in the unit cell is M is equal to capital M divided by Na. Capital M is the molar mass. Therefore, density of the unit cell is equal to mass of unit cell divided by volume of unit cell is equal to Z into M divided by A cube. Z into capital M divided by A cube into Na, or D is equal to Zm divided by A cube Na. Remember, the density of the unit cell is the same as the density of the substance. The density of the solid can always be determined by other methods. Out of the 5 parameters Z, D, M, A and Na, if any 4 are known, we can determine the fifth. 1.9 Imperfections in solids. Although crystalline solids have short range as well as long range order in the arrangement of their constituent particles, yet crystals are not perfect. Usually, a solid consists of an aggregate of large number of small crystals. These small crystals have defect in them. This happens when crystallization processes occurs at fast or moderate rate. Single crystals are formed when the process of crystallization occurs at the extremely slow rate. Even these crystals are not free of defects. The defects are basically irregularities in the arrangement of constituent particles. Broadly speaking, the defects are of two types, namely point defect and the line defect. Point defects are the irregularities or deviation from the ideal arrangement around a point or an atom in a crystalline substance, whereas the line defects are the irregularities or deviation from the ideal arrangement in entire rows of lattice points. These irregularities are called crystal defects. We shall confine our discussion to point defects only. 1.9.1 Types of defects. Point defects can be classified into three types. First, stoichiometric defects, second, impurity defects, and third, non-stoichiometric defects. First, stoichiometric defects. These are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects. Basically, these are of two types, vacancy defects and interstitial defects. First, vacancy defect. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This results in decrease in density of the substance. This defect can also develop when a substance is heated. Second, interstitial defect. When some constituent particles, atoms or molecules occupy an interstitial site, the crystal is said to have interstitial defect. Figure 1.28. This defect increases the density of the substance. Vacancy and interstitial defects are explained above can be shown by non-ionic solids. Ionic solids must always maintain electrical neutrality rather than simple vacancy or interstitial defects. They show these defects as Frankel and Schottky defects. Third, Frankel defect. This defect is shown by ionic solids. The smaller ion, usually cation, is dislocated from its normal site to an interstitial site. It creates a vacancy defect at its original site and an interstitial defect at its new location. Frankel defect is also called dislocation defect. It does not change the density of the solid. Frankel defect is shown by ionic substance in which there is a large difference in the size of ions. For example, ZnS, AgCl, AgBr and AgI due to small size of Zn plus 2 and Ag plus ions. Fourth, Schottky defect. It is basically a vacancy defect in ionic solids. In order to maintain electrical neutrality, the number of missing cations and anions are equal. Figure 1.30. Like simple vacancy defect, Schottky defects also decreases the density of the substance. Number of such defects in ionic solids is quite significant. For example, in NaCl there are approximately 10 to the power 6 Schottky pairs per centimeter cube at room temperature in 1 centimeter cube. There are about 10 to the power 22 ions, thus there is 1 Schottky defects per 10 to the power 16 ions. Schottky defects is shown by ionic substance in which the cation and anions are of almost similar sizes. For example, NaCl, KCl, CaCl and AgBr. It may be noted that AgBr shows both Frankel and as well as Schottky defects. Impurity defects. If molten NaCl containing a little amount of SrCl2 is crystallized. Some of its sites of Na plus ions are occupied by Sr plus 2. Figure 1.31. Figure 1.31. Introduction of cation valency in NaCl by substitution of Na plus by Cr plus 2. Each Cr plus 2 replaces two Na plus ions. It occupies the site of one ion and the other site remains vacant. The cationic vacancies that produced are equal in numbers to that of Sr plus 2 ions. Another similar example is the solid solution of CdCl2 and AgCl. C. Non-stoichiometric defects. The defects discussed so far do not disturb the stoichiometry of the crystalline substance. However, a large number of non-stoichiometric inorganic solids are known, which contain the constituent elements in non-stoichiometric ratio due to the defects in the crystal structures. These defects are of two types. First, metal excess defect, and second, metal deficiency defect. First, metal excess defect. Metal excess defect due to anionic vacancies. Alkaline halides like NaCl and KCl show this type of defects. When crystals of NaCl are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of crystal. The Cl- ions diffuses to the surface of the crystal and combine with Na atoms to give NaCl. This happens by loss of electron by sodium atoms to form Na plus ions. The released electron diffuses into crystal and occupy anionic sites. Figure 1.32. Figure 1.32. An F center in a crystal. As a result, the crystal now has an excess of sodium. The anionic sites occupied by unpaired electrons are called F centers, from German word Farbencenter for color center. They impact yellow color to the crystal of NaCl. The color results by excitation of these electrons when they absorb energy from the visible light falling out on the crystal. Similarly, excess of lithium makes LiCl crystal pink and excess of potassium makes KCl crystal violet or lilac. Metal excess defect due to the presence of extra cations at interstitial sites. Zinc oxide is white in color at room temperature. On heating, it loses oxygen and turns yellow. ZnO on heating give rise to Zn plus 2 plus 1 by 2 O2 plus 2 electrons. Now there is excess of zinc in the crystal and its formula becomes Zn1 plus x 0. The excess Zn plus 2 ions move to interstitial sites and the electrons to neighboring interstitial sites. Second, metal deficiency defect. There are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of metals as compared to stoichiometry proportion. A typical example of this type is FeO, which is mostly found with a composition of Fe 0.950. It may accurately range from FeO 0.930 to Fe 0.960. In the crystal of FeO, some Fe plus 2 cations are missing, and the loss of positive charge is made by the presence of required numbers of Fe plus 3 ions. 1.10. Electrical properties. Solid exhibit an amazing range of electrical conductivities extending over 27 orders of magnitude, ranging from 10 to the power minus 20 to 10 to the power 7 ohm meter m to the power minus 1. Solid can be classified into three types on the basis of their conductivities. First, conductors. The solid with conductivities ranging between 10 to the power 4 to 10 to the power 7 ohm meter m to the power minus 1 are called conductors. Metals having conductivities in the order of 10 to the power 7 ohm meter m to the power minus 1 are good conductors. Second, insulators. These are the solids with very low conductivities ranging between 10 to the power minus 20 to 10 to the power minus 10 ohm meter m to the power minus 1. Third, semiconductors. These are the solids with conductivities in the intermediate range from 10 to the power minus 6 to 10 to the power 4 ohm meter m to the power minus 1. 1.10.1 Conduction of electricity in metals. A conductor may conduct electricity through movement of electrons or ions. Metallic conductor belong to the former category and electrolytes to the later. Metals conduct electricity in solid as well as molten state. The conductivity of metals depend upon the number of valence electrons available per atom. The atomic orbitals of metal atoms from molecular orbitals which are so close in energy to each other as to form a band. If this band is partially filled or it overlaps with higher energy unoccupied conduction band, then electrons can flow easily under an applied electric field and the metal shows conductivity. Figure 1.33a. If the gap between filled valency band and the next higher unoccupied band, conduction band is large, electrons cannot jump to it, and such a substance has very small conductivity and it behaves as an insulator. Figure 1.33b. 1.10.2 Conduction of electricity in semiconductors. In case of semiconductors, the gap between the valence band and conduction band is small. Figure 1.33c. Therefore, some electrons may jump to conduction band and show some conductivity. Electrical conductivity of semiconductors increases with rise in temperature since more electrons can jump to the conduction band. Substances like silicon and germanium show this type of behavior and are called intrinsic semiconductors. The conductivity of these intrinsic semiconductors is too low to be of practical use. Their conductivity is increased by adding an appropriate amount of suitable impurity. This process is called doping. Doping can be done with an impurity which is electron rich or electron deficient as compared to the intrinsic semiconductors, silicon or germanium. Such impurities introduce electronic defects in them. A. Electron rich impurities. Silicon and germanium belong to group 14 of the periodic table and have 4 valence electrons each. In their crystals, each atom forms 4 covalent bonds with its neighbor. Figure 1.34a. When doped with a group of 15 elements like P or As which contains 5 valence electrons, they occupy some of the lattice site in silicon or germanium crystal. Figure 1.34b. 4 out of 5 electrons are used in the formation of 4 covalent bonds with the 4 neighboring silicon atoms. The 5th electron is extra and become delocalized. These delocalized electrons increase the conductivity of doped silicon or germanium. Here, the increase in the conductivity is due to the negatively charged electron. Hence, silicon doped with the electron-rich impurities is called N-type semiconductors. B. electron deficient impurities. Silicon or germanium can also be doped with group 13 elements like Ba, Al or Ga, which contains only 3 valence electrons. The place where the 4th valence electrons is missing is called electron hole or electron valency. Figure 1.34c. An electron from a neighboring atom can come and fill the electron hole, but in doing so it would leave an electron hole at its original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of electron that filled it. Under the influence of electric field, electrons would move towards the positively charged plate through electronic holes, but it would appear as if electron holes are positively charged and are moving towards negatively charged plate. This type of semiconductors are called p-type semiconductors. Figure 1.34. Creation of n-type and p-type semiconductors by doping groups 13 and 15 elements. Applications of n-type and p-type semiconductors. Various combinations of n-type and p-type semiconductors are used for making electronic components. Diode is combination of n-type and p-type semiconductors and is used as a rectifier. Transistors are made by sandwiching a layer of one type of semiconductor between two layers of the other type of semiconductor. NPN and PNP type of transistors are used to detect or amplify radio or audio signals. The solar cell is an efficient photodiode used for conversion of light energy into electrical energy. Germanium and silicon are group 14 elements and therefore have a characteristics valence of 4 and form 4 bonds as in diamond. A large variety of solid state material have been prepared by combination of group 13 and 15 or 12 and 16 to stimulate average valence of 4 as in Ge or Si. Typical compounds of group 13-15 are in Sb, AIP and GaAs. Gallium arsenide GaAs semiconductors have very fast response and have revolutionized the design of semiconductor devices. ZNS, CDS, CDSE and HGTE are examples of group 12 to 16 compounds. In these compounds, the bonds are not perfectly covalent and the ionic character depends on the electronegativities of the two elements. It is interesting to learn that transition metals oxides show marked difference in electrical properties. TiO, CrO2 and ReO3 behave like metals. Rhenium oxide ReO3 is like metallic copper in its conductivity and appearance. Certain other oxides like VO, VO2, VO3 and TiO3 show metallic or insulating properties depending on temperature. 1.11 Magnetic properties. Every substance has some magnetic properties associated with it. The origin of these properties lies in the electrons. Each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from two types of motions. First, its orbital motion around the nucleus and second, its spin around its own axis. Figure 1.35. Electron being charged particles and undergoing these motions can be considered as a small loop of current which possesses a magnetic moment. Thus, each electron has a permanent spin and an orbital magnetic moment associated with it. Magnitude of magnetic moment is very small and is measured in the unit called Bohr magneton. Nu B, it is equal to 9.727 into 10 to the power minus 24 a meter square. On the basis of their magnetic properties, substances can be classified into 5 categories. First, paramagnetic. Second, diamagnetic. Third, ferromagnetic. Fourth, antiferromagnetic. And fifth, ferrimagnetic. First, paramagnetism. Paramagnetic substances are weakly attracted by the magnetic field. They are magnetized in magnetic field in the same direction. They lose their magnetism in the absence of magnetic field. Paramagnetism is used to presence of one or more unpaired electrons which are attracted by the magnetic field O2, Cu plus 2, Fe plus 3, Cr plus 3 are some examples of such substances. Second, diamagnetism. Diamagnetic substances are weakly repelled by a magnetic field. H2O, NaCl and C6H6 are some examples of such substances. They are weakly magnetized in magnetic field in opposite direction. Diamagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Pairing of electrons cancels their magnetic movements and they lose their magnetic character. Third, ferromagnetism. A few substances like iron, cobalt, nickel, gadolinium and CrO2 are attracted very strongly by magnetic field. Such substances are called ferromagnetic substances. Besides strong attraction, these substances can be permanently magnetized. In solid state, the metal ions of ferromagnetic substances are grouped together into small regions called domains. Thus, each domains act as a tiny magnet. In an unmagnetized piece of a ferromagnetic substance, the domains are randomly oriented and their magnetic movements get cancelled. When the substance is placed in a magnetic field, all the domains get oriented in the direction of magnetic field. Figure 1.36a. And a strong magnetic effect is produced. This ordering of domains persists even when the magnetic field is removed and the ferromagnetic substance becomes a permanent magnet. Fourth, antiferromagnetism. Substances like MnO showing antiferromagnetism have domain structure similar to ferromagnetic substance, but their domains are oppositely oriented and cancel out each other's magnetic movement. Figure 1.36b. Fifth, ferrimagnetism. Ferrimagnetism is observed when the magnetic movements of the domain in the substance are aligned in parallel and antiparallel directions in unequal numbers. Figure 1.36c. They are weakly attracted by magnetic fields as compared to ferromagnetic substances. Fe3O4 magnetite and ferrites like MgFe2O4 and ZnFe2O4 are examples of such substances. These substances also loses ferrimagnetism on heating and become paramagnetic. Figure 1.36. Schematic alignment of magnetic movements in A. Ferromagnetic, B. Antiferromagnetic and C. Ferrimagnetic. Thank you for being till the end. I hope this has helped you. If so, give thumbs up, like, share, comment, save, download and subscribe. You can support us by following in other platforms. That link is in the description. Well, thank you. See you later. Maybe never.